everyone. This is a quick video on just showing that sample variance is biased. So another way to approach this is thinking about the MLEs of a normal distribution for parameters sigma squared and mu. These are the MLE estimates, which I already have written out. So we're showing that this particular MLE estimate is going to be biased. Now what bias means is that the expected value of the estimator minus the estimator is not 0. So we are showing, another way of saying that is saying expected value of the estimator and the estimator is not equal. So to do that, we just take the expected value of that estimator, which is the expected value of sigma squared, which is the expected value of 1 over n, I from 1 to n xi minus x bar squared. And 1 over n comes out. It's a property of expected values. Now, because of this square term, we actually have to factor out what's inside the parentheses. So this becomes the expected value I from 1 to n xi squared minus 2 xi x bar plus x bar squared and in bracket. Then we have, let's see if I can, factoring this out, we're simplifying this a little bit more. We have I equals 1 to n xi squared minus 2 sum I equals 1 to n xi x bar plus x bar squared. This gives us 1 times n expected value bracket sum I equals 1 to n xi squared minus, so this term right here essentially becomes, this should be times n. We can times this by 1 or n times n, then we get 2n x bar times x bar, which is just x bar squared, plus x bar squared times n, which becomes 1 over n expected value I equals 1 to n xi squared minus x bar squared times n. Now, I've been trying to be a little careful with this and make sure it's really obvious what's going to be happening here. So quick break from the proof, recall that the variance of x, of just any x here, so I could say xi, is equal to the expected value of xi squared minus the expected value of xi squared, where the square is outside of the expected value, which implies that the expected value of xi squared is equal to the variance of xi plus the expected value of xi with the square term outside of the expected value. Now this becomes sigma squared plus mu squared. In a similar idea, we have the variance of x bar is also equal to the expected value of x bar, and this would be square inside the expected value, minus the expected value of x bar and with the square outside the expected value. We can think of x bar as actually its own unique random variable. So you can even just denote it y if that helps you think about it as a unique random variable. Now if you remember, the variance of x bar actually ends up being sigma squared over n. x bar squared is what's unknown, that's what we're trying to figure out. And then we have the expected value of x bar squared. We know that mean is an unbiased estimator for mu, so this just becomes, this should be a positive. This just becomes mu squared, which gives us that the expected value of x bar squared is equal to sigma squared over n plus mu squared. So using this information, we can go back to our formula and continue on with the proof. So we have the expected value of the sum of the expected value of xi squared ends up just being 1 over n, and this first term is n times sigma squared plus mu squared, which we're getting from here. The next term is minus, and this would be this whole expression times n, so n times sigma squared over n plus mu squared. We can see that these n's cancel out, so we're done with these n's, and we get sigma squared plus mu squared minus sigma squared over n minus mu squared, which is equal to sigma squared minus sigma squared over n, which is equal to sigma squared 1 minus 1 over n, which is not equal to sigma squared, which is why we have a biased estimator. So another way of writing this is also sigma squared n minus 1 over n, which is why we say sigma squared hat. Why we use the estimator 1 over n minus 1, sum I equals 1 to n xi xi minus x bar squared, and we use that as our unbiased estimator.